Reality feels settled, but in this video, we will move carefully from the familiar worlds we know into the strange rules that govern reality beneath it, one idea at a time. It feels as though the universe has already made up its mind about how things fall, how time moves forward, how objects exist, whether or not we pay attention to them. Most of our lives unfold inside this quiet assumption that the world is simply there, complete and independent of us. But physics has discovered something unsettling beneath that surface. At its deepest level, reality does not behave like a finished picture. It behaves more like a question. Look around you. This world feels solid, reliable, predictable. You drop your phone and it falls. It doesn't hover. It doesn't drift left. It plummets to the floor with a certainty that borders on boring. Your alarm clock rings on time every morning. The coffee brews. The engine starts. The sun rises. It's a world of dependable physics, cause and effect, clockwork certainty. For centuries, this predictable view of reality was our bedrock. It's how we built skyscrapers, launched satellites. It is the reality of our daily lives. But it is not the whole reality. Beneath this solid surface, in the subatomic depths, the universe operates on rules so bizarre, so alien to our intuition, that they seem impossible. We're talking about particles that exist in two places at once, about measurements that don't just reveal reality, but somehow create it, about the unsettling possibility that the future can reach back and influence the past. This is not science fiction. This is quantum mechanics. It is the most accurate, rigorously tested scientific framework in human history. Its predictions have been confirmed to 15 decimal places. It powers the lasers in your devices, the transistors in your computer, the GPS in your phone. Without it, modern civilization would not exist. And yet, for 100 years, the scientists who use it have been forced to admit a profound truth. We can calculate with it perfectly, but nobody truly understands what it means. This is the story of that mystery. In our everyday world, observation is passive. You'll look at a mountain, and the mountain doesn't change. You read a thermometer, the temperature stays the same. Looking reveals a world that is already there. But quantum mechanics shatters this assumption. At the quantum scale, looking isn't passive. It's a form of participation. And the simplest, most devastating proof of this is a century-old experiment, the double-slit experiment. Picture a barrier with two thin, parallel slits. Behind it, a detector screen. We fire tiny particles, electrons, one at a time, at this barrier. Classical expectation says if electrons are little bullets, they should go through either the left slit or the right slit, piling up in two bands on the screen. But that's not what happens. When we don't watch which slit the electron goes through, we don't see two bands. We see a series of light and dark stripes, an interference pattern. This is the unmistakable signature of a wave, like ripples from two stones in a pond. Each electron seems to go through both slits at once, spreading out as a wave, interfering with itself on the other side. Each individual electron fired alone is somehow in a superposition, a genuine state of being in multiple places simultaneously. Now here's the twist. We put a detector at the slits. We want to catch the electron in the act. We place a device to tell us definitively which path it takes. The instant we do this, the interference pattern vanishes. The screen now shows only two bands. The electrons, now under surveillance, stop behaving like mysterious waves and start behaving like particles, going through one slit or the other. They choose a definite path. The mere act of asking the question, which path did you take, forces the electron to answer that question. The potential to know changes the behavior. The universe seems aware of the context of our inquiry. This is the heart of the measurement problem. Quantum mechanics describes particles before measurement with a mathematical wave function, a cloud of probabilities spreading and evolving in smooth, deterministic fashion. But the moment a measurement happens, that wave function collapses. All those possibilities vanish, and a single concrete outcome snaps into existence. And here's the question the theory leaves utterly unanswered. What exactly is a measurement? When does it happen? Is it the click of a detector? The firing of a neuron in a human brain? The interaction with a single atom? The equations are silent. They give us perfect odds, but no explanation of how the winner is chosen. As physicist Richard Feynman put it, if you think you understand quantum mechanics, you don't understand quantum mechanics. Niels Bohr, one of its architects, said those who are not shocked when they first come across quantum theory cannot possibly have understood it. We have a map that works flawlessly, but we don't speak the language of the territory. If the simple act of looking changes the present, what happens when we play tricks with time? What if we delay our decision of what to look for until after the quantum event should be over? This leads us to one of the most philosophically devastating experiments in science, the delayed choice quantum eraser. We create a pair of entangled photons, quantum twins, whose fates are linked, no matter how far apart they are. We'll call them signal and idler. Signal photon goes toward our double-slit setup. Idler photon takes a different path to its own set of detectors. Here's the quantum magic. By measuring the idler photon in clever ways, we can infer which path information about its twin, the signal photon, without ever touching the signal photon itself. Now for the time-bending part. We set it up so that the signal photon completes its entire journey first. It goes through the slits, flies across the lab, and hits the final detection screen, leaving a permanent mark. Its fate, it seems, is sealed in history. Only then, milliseconds later, do we decide what to do with its entangled twin, the idler photon. Our choice with the idler is this: measure it to get which path information, or measure it in a way that erases all possibility of ever getting which path information. The impossible result? When scientists sort through the data, matching each signal photon hit with what we later did to its idler twin, they find this. If we chose to get which path information from the idler, the signal photons on the screen behaved like particles. 2 bands, no interference. If we chose to erase that information from the idler, the signal photons on the screen behaved like waves, interference pattern. Our choice in the present appears to have retroactively determined the past behavior of the particle. The photon's decision about whether to be a wave or a particle seems to depend on a choice we haven't made yet. Let's be clear. This does not allow for sending messages to the past or changing history. The universe has safeguards, but it forces us to rethink our notion of time and causality. Perhaps time and the quantum level is not a one-way street. Perhaps past, present, and future are more like a completed landscape, and our conscious experience is just a spotlight moving across it. Our delayed choice was always part of the fixed geometry of the event. This is the crack that runs straight through our sense of history. If measurement creates reality and the timing is fluid, what happens when 2 different observers have access to different information? Can they see 2 different contradictory realities and both be right? This is the premise of Wigner's Friend, a thought experiment from 1961 that has recently been tested in laboratories. Imagine a sealed lab. Inside, a scientist, call her Alice, performs a measurement on a quantum particle in superposition, say spinning both clockwise and counterclockwise. She looks at her detector. It reads clockwise. For Alice, inside the lab, the collapse has happened. The particle is definitively clockwise. She writes it in her logbook. Reality for her is concrete. Now outside the lab stands another scientist, Wagner. He has not opened the door. He has not seen Alice's result. According to the mathematics of quantum mechanics, from Wagner's perspective, the entire lab, Alice, her detector, the particle, must still be in a superposition of states. From his outside view, there is no single outcome yet. There is an Alice who saw clockwise and an Alice who saw counterclockwise, both existing in a blurred quantum state until he opens the door and makes his own observation. Who is right? Alice says the particle is clockwise. She saw it. Collapse happened. Wagner says the system is still in superposition. No collapse has occurred until he looks. Both are following the rules of quantum mechanics correctly from their own reference frame. Yet they have fundamentally incompatible descriptions of objective reality. Recent experiments using tiny quantum systems as proxy observers have confirmed this paradox. Different parts of experimental apparatus can record contradictory facts about the same quantum event, with each record being internally consistent. This isn't about human perception or error. This suggests that objective reality, the idea that there is one single agreed upon state of the world, might be an illusion. Reality might be observer dependent, fragmenting along the lines of who is measuring, when, and what they know. The many worlds interpretation offers one solution. Both Alice and Wagner are right. When Alice measured, the universe splits. One branch contains Alice who saw clockwise, another contains Alice who saw counterclockwise. Wagner, still outside, is in a superposed state, linked to both branches. When he opens the door, he splits as well, walking into one branch to meet one Alice, and into another branch to meet the other. We don't experience the splitting. We only experience one branch. But this interpretation suggests that with every quantum event, reality endlessly branches, creating a multiverse of staggering proportions. The crack has become a chasm, dividing not just particles, but consciousness itself. Amidst all this fragmentation, quantum mechanics reveals a counterpoint, a profound, invisible unity. This is quantum entanglement. Two particles can be created or interact in such a way that their quantum states become inextricably linked. Measure one, and you instantly know the state of the other, no matter if it's on the other side of the lab or the other side of the galaxy. This isn't just correlation. Experiments have definitively ruled out the possibility of hidden instructions. The connection is immediate and non-local. Einstein hated this, calling it spooky action at a distance. But it's real. This unity leads to effects that mock classical logic. In quantum pseudo-telepathy games, two players with entangled particles can achieve a perfect, synchronized strategy that would be mathematically impossible using only classical physics. They win 100% of the time, not through secret signals, but because their particles are, in a deep sense, parts of a single quantum system. Their choices are correlated by the underlying fabric of reality itself. It gets stranger. In the quantum Cheshire Cat experiment, physicists have set up scenarios where a particle and one of its key properties appear to become spatially separated. Through clever, weak measurements, it seems the particle travels down one path while its spin travels down another, like the grin of the Cheshire Cat floating apart from the cat itself. This suggests that in the quantum world, properties may not be permanently attached to objects in the way our classical minds assume. These phenomena tell us that the quantum realm is not a collection of separate billiard balls. It is a web of relationships. What we call objects may be temporary knots in this web, and what we call properties may be patterns of connection that can, under the right conditions, be teased apart. The crack reveals not just emptiness, but a tapestry of connection far deeper than we imagined. So, where does this leave us? We've journeyed from a solid, predictable world into a realm where measurement creates as much as it reveals, where time may be an emergent property, not a fundamental flow, where objective reality may shatter into observer-dependent perspectives, where separateness may be an illusion, beneath which lies a universe of non-local connections. Quantum mechanics forces a humbling and exhilarating conclusion. We are not passive observers of a pre-existing external reality. We are participants. The questions we choose to ask of the universe, which path, which spin, when do we look, don't just uncover answers that were already written. They help determine which answers become written. The universe seems to require this interaction to crystallize from a fog of possibilities into the definite world we experience. This doesn't mean we can wish reality into existence. The constraints are rigid, the mathematics exact. But within those constraints, there is a dialogue, a universe that is relational, contextual, and deeply, strangely interactive. The quantum pioneers were shocked because they discovered that to understand the cosmos, we must also understand the role of the observer. And that ultimately includes us. We are not outside the system looking in. We are embedded within it, and our awareness, our measurement, our very act of questioning is part of the cosmic process that brings reality into sharp focus. This is the ultimate message from the quantum realm. It is a place of profound mystery, yes, but it is also a place of profound intimacy. We are not strangers in a cold mechanical universe. We are partners in a cosmic dance of possibility and actuality, helping to shape through our observation and our science the very reality we seek to understand. The cracks in our classical world are not signs of brokenness. They are windows, and through them we are glimpsing a universe far stranger, more interconnected, and more wonderful than we ever dared to dream.